So last week we talked about forces and momentum, right? Forces are vectors. They have a magnitude and a direction, and they describe a push or a pull. And they change the motion of an object. And when I say motion, I mean momentum. But if there is no net force on an object, then its motion or momentum does not change. If there is a net force, then its motion or momentum will change. So what is momentum? Well, it's not just the velocity of an object, it's speed and in what direction, but it also has to do with the mass of it, right? If I have a heavy object and a light object moving with the same velocity, the heavy object is going to carry more momentum. And you can experience that just by if I tossed you a golf ball and tossed you a bowling ball with the same velocity, you're going to feel the bowling ball a lot more because it carries more momentum. And so another way to say that, it would deliver a larger impulse to you, right? Impulse describes a transfer of momentum. It has the same units. It's really the same concept. You can get away in this class without ever using J net if you really wanted to, because J, like impulse, is just a way to describe, again, a transfer of momentum. So an F net delta t, a force applied over a time, delivers an impulse, J net, and an impulse, J net, causes a change in momentum, delta p, right? So it's just kind of like this intermediate quantity, a vocabulary word really is all it is. But it's just used to describe the transfer of momentum that occurs when you apply a force over a time and change an object's momentum. Delta p, quite literally meaning the change of an object's momentum. The delta p is the difference between our initial and our final. Like I mentioned before, you only get a change in momentum with a force, and the converse is true. If there's no force, you don't get a change in momentum. That says nothing, though, about what the initial value of momentum is. You can have a constant momentum without a force. So if my P initial is something, and then I have no net force, my P initial doesn't have to be 0. It just has to be whatever the P initial was. So if you have an object moving with a constant velocity, you do not need any force. In fact, you know that there's no force that is sustaining that. Another key thing to mention is that a change in velocity doesn't necessarily have to include a change in speed, right? If I have an object moving and I apply a force that slows it down or speeds it up, that's clearly a change in velocity. But also, something that turns it without changing its speed is still a change in velocity. And a change in momentum as well. We need a force to cause any change to the velocity and the momentum, which again can include a direction change, a magnitude change, or both. We're also starting to work with systems of objects. So the only that's not true, but one of the complexities beyond that, to get the total momentum, we just sum up all the momenta of the individual objects. And then that total momentum behaves with the same rules that we just discussed. If the net force on the whole system is 0, the total momentum is constant. If the net force is not 0, the total momentum changes in accordance with the same equation that we had before. I guess another complexity there is that even though the total may not change, there can still be exchanges of momentum between the individual objects in the system, right? Each one doesn't have to stay constant, just their total. And that's something that we'll look at a lot today. But before we go to a system of objects, let's just take a look at one case where we have an object with two forces that act on it in succession. So we have this object A, this box, 3 kilograms, and it's at rest, right? So our initial velocity, our initial momentum are 0, and then we act on it with F1 to the right that has the components 3, 0 newtons, and then afterwards, we apply F1 for 2 seconds, and then afterwards, we apply F2, which is a force directed downward, for 3 more seconds. And we want to ask, what is the magnitude and direction of the object's final velocity? So what effect do these two forces applied in succession have on this object's motion? So something I always recommend we start with is a momentum chart. I think I said this last time and on Piazza, but we're not going to grade you on momentum charts. I'm not going to explicitly ask you for them. You will in DL, but never on an assessment. They're just a tool for you to use. I think they're very helpful, and I recommend them. But if they don't work for you, then don't use them. That's fine. But let's try it together. like we said, our P initial is 0. We just have a box sitting there at rest, velocity 0, momentum 0. Then we apply two forces to it, one and then the other. But we only have one delta P column, right? I have two forces. That's something we haven't really seen before. One force acts, and then another force acts. How do I work with that in the context of this tool? Well, let's go back to something we talked about a lot early in this quarter, is really being specific about what my initial and my final are. So far, we've just had kind of single instances. I apply one force, so my initial is before the force, my final is after. Same thing with like collisions and stuff. Before the collision, after the collision, it's very clear what my initial and final is. But here, there's a couple things happening, right? I have something at rest, then I apply one force, and then another. And it doesn't matter as long as I still take my initial before any of the forces acted, and then I take my final after they're all done. And if that's true, it doesn't matter whether or not F2 and F3 or F1 and F2 happen at the same time. If F1 happens, then immediately after F2 happens, or if F1 happens and then 600 years pass and then F2 happens, it doesn't matter as long as we know that these are the forces that acted on the object, and this is the result, right? We just want to know what happens to the object if I apply these impulses to it, right? And it's just kind of irrelevant when they occur, so long as my initial is before they do, and our final is after they both do. So I'm going to treat these impulses as if they were occurring just together sometime during delta P. And so even though they're not simultaneous, my Fnet is still just F1 plus F2. So how do I take Fnet and make it into a delta P? Well, Fnet times delta T, right? It's just a force delivered over a change in time, gives us a change in momentum. So the direction of delta P that I can draw on here, my change in momentum arrows, will just be in the same direction as whatever my Fnet is. And so to do that, I'll just add vectors, right? F1, or really the impulse delivered by F1, is to the right, and the impulse delivered by F2 is down. And so if we add those vectors together, we get something that is down and to the right. I'm not super concerned with scaling here because I'm just trying to get an overall idea of what's happening. So now I start with 0, an object at rest. I apply this impulse, even though it's made of two different forces at two different times. The total impulse that I'm delivering, right? It's just how much momentum am I pouring into this object is this. And so that object's final momentum is just going to be whatever I added to it with the forces over time. Okay, so now let's turn this into some algebra. So the real thing we need to figure out is what is this delta P, right? We're just adding 0 plus delta P equals P final. Or in other words, whatever our P final is equal to this delta P. What impulse do I deliver using these forces? And like we said a few times, delta P is just Fnet times delta T. This is a vector equation, but we know it's much easier to just work with components, right? So these two equations, the second one's just the definition of momentum, are really two separate ones. There's one completely separate from the x direction. My change in momentum in the x direction is equal to the impulse delivered in the x direction, and separately for the y. And it just so happens that this also breaks down into the two different forces, right? Where is my impulse in the x direction coming from? Well, that's just coming from F1. Where is my impulse in the y direction coming from? That's just coming from F2. Okay? So what are the components of my Fnet? Well, if we add those two together, it's pretty simple. They're already broken down into components for us. So 3 plus 0 is 3. 0 plus negative 4 is negative 4. So that's the Fnet vector, this down and to the right vector that we found before. One complexity here is that they don't act for the same amount of time, right? So maybe I could have done a better job with notation here. I have delta t here, but these specifically are the delta t, the amount of time that my net force in the x direction is occurring for. Usually we don't often see these as separate amounts of time, but here my delta t x is 2 seconds, right? F1 acts for 2 seconds, and my delta t for the y is 3 seconds. We're told F2 acts for 3 seconds. So we'll have to evaluate those slightly differently. Yeah, so that's just something to be aware of. Okay, so let's do the x direction. Delta px is f net x delta t. So we plug in our f net x, which is 3 newtons, and it acts for 2 seconds. And so we get an impulse delivered, or a change in momentum in the x direction of 6 kilograms meters per second. And then this line's kind of trivial. This is just us reiterating that whatever my final momentum is just equal to the delta p, right? Because p final is p initial plus delta p. P initial is 0. So P final is just whatever that delta P was, or 6 kilogram meters per second. And then lastly, we're asked about the velocity, not the momentum. So to go back and forth between them, we just divide by mass, right? Velocity is momentum divided by mass. So we find that from the impulse delivered in the x direction, the object's final velocity in the x direction is 2 meters per second. All right, now let's do the same for the y direction. Very similar work, except now the y component that I'm plugging in is -4, and it acts for 3 seconds instead of 2. A key thing to note, now we're working in magnitudes, right? In x and y directions, it's not really vectors anymore, but we still, despite us not working with vectors, we still do need to pay attention with signs, right? Because even though we're only dealing with individual directions, I still have right and left and up and down separately. So it is important that this is negative. And we get an impulse delivered of -12 kilogram meters per second in the in the y direction. So working through the same, if that's the impulse delivered, that's our final momentum for the object. And dividing by mass, we find that the final velocity of the object from the impulse delivered in the y direction is -4 meters per second in the y direction. So putting that together with our x answer, we get our final velocity is 2 meters per second in the x direction, -4 in the y. And this would be the same answer whether the forces acted simultaneously, one after the other, one 600 years in the other. It doesn't matter. We have an object with 0 momentum. That's our whole system. Nothing else is acting on it. Then I apply these 2 forces, which each of them, over some amount of time, delivers some amount of impulse. Nothing else matters here. Just what impulse did I dump into it? That's our change in momentum. Then finally, we want the magnitude and direction of the object's final velocity, so we have to convert from these components. Well, maybe visually this will help a little bit if we draw it out. Our x and y components represent components, but the size of the triangle. And then the hypotenuse is going to give us the magnitude. So we need to use the Pythagorean theorem for that. And we just take the square root of 2 squared plus -4 squared. We get 4.47 meters per second. And then the trickier part is finding the direction. We know it's going to be down and to the right, but there's a couple ways to describe that. So the angle I've labeled here to start with is one way we can describe this theta is south of east, right? East points to the right, south rotate down from that. I could also say that is clockwise from the positive x direction, or clockwise from east. It doesn't matter. Any way you describe the angle, so long as you give your reference and then what direction you're going. So south of east gives me my reference is east, and I'm going south from it. We've had a lot of practice with that at this point. So how do we actually solve for theta? Well, this theta has v1y as its opposite side and v1x as its adjacent, right? So for the tangent of v1y over v1x will give us this theta, or the inverse tangent of those. So if we solve this, we get theta. The theta that I've labeled is 63.4 degrees, and like we said, this is south of east. That's just one way we could do it, though. I could also have labeled this angle theta. This triangle is made up of the same y component and x component, right? I just added them in a different order graphically. And this triangle is equally fine. They give the same v final vector, but the angle I've labeled now is one that is east of south, or counterclockwise from -y, so on and so forth. And for this one, the theta that I've labeled now x is the opposite, and y is the adjacent. So instead of tan theta equals 4 over 2, I get tan theta equals 2 over 4, which is 36.6. And of course, 36.6 is the complement of 63.4. They add up to 90 degrees. It just depends. We have one quadrant, and we're just giving an angle in relation to either the positive x-axis or the negative y-axis. Both are equally correct. They say the same thing. They describe this same v final vector. Again, the key part is just you need to tell us what angle you're talking about when you give an answer. Okay, questions about this problem? The key takeaways I wanted to do were just do an extra practice using some trig, and then drive home the initial final thing, that these two forces, even though they're occurring in succession, not at the same time, it works the same way. We're delivering a total amount of impulse to an object. All right, let's change gears a little. Let's do a clicker question. We have an object, a ball that's moving with this momentum vector moving up, and it has a firecracker in it that explodes at some point, and it breaks up into three pieces. Which of these scenarios for the final momenta of all the pieces does not conserve momentum? So which one of these is impossible or requires an external force? So we have a ball moving, it explodes, no other force is present. Which one of these final scenarios is not possible or does not conserve momentum? All right, I'm going to not give away the answer yet, but let's just regroup for a sec and decide together what it would mean for momentum to be conserved here. So momentum conservation means that our initial total momentum is the same as our final total momentum. And our initial total momentum, we just have one object, it's this vector here. So what the question is asking is which one of these has a total momentum that is not equal to what we started with. I'll give you another 30 seconds or so to think about that one. All right. So I saw a few people change toward the right answer. Let's work through it quickly together. So like we said, we want the total momentum in the final state to equal the total momentum in the initial because there's no external force. So let's look at A. We've introduced some x components, right? We started with our x component and the momentum being 0. We just have a vector pointing up. However, the x components appear to be equal and opposite. So those will just cancel out, and we're left with this one vector pointing up, which that works out. Our total is just a vector pointing upward. Let's just go down. What about C? C now very similar, except the ones that are pointing out are also pointing up a little bit. So same thing, equal and opposite in the x direction. This one points left just as much as this one points right. So x still cancels, that's fine. Except now we have a little bit of up coming from each one of the ones on the left and right, and the vector on top has shortened a little, which is still fine, right? Because before we just had a single large vector pointing up, and now we have 3 smaller y components that are adding up to give us this bigger total y, which is what we want. E, now this is the ones on the left and right the y component has grown, but this top one has flip-flopped from pointing up to down. So let's try to use our, well, first x components still, that works out, they cancel, right? Even though this one points a bit left, this one points a bit right, they cancel, and so we just need to look at the y. This one on the left, has a positive y component. That's pretty big, right? And that's about the same. They all, if you look, have pretty much the same magnitude of their y component, right? This one on the left goes up just as much as this middle one goes down, and just as much as this one on the right goes up. So if we add them all together, I have like a +1, -1, and then a +1. So my net is still just one large vector upward, which is what we want. So E works also. B, okay, similar reasoning. X still cancels out, right? But the one now we have, again, the y components all have similar the same magnitude, but now we have 2 downs and 1 up, right? So our net here is actually down. So B is our answer. B does not have the same total momentum as our initial because, like I said, the net y component is down, even though the x cancels. And then D, I mean, there's just 3 small vectors pointing up, which add up to 1 larger vector pointing up. That's all good. Okay, so why did we do this? Well, kind of just to practice 2 concepts that will be helpful for momentum charts if you decide to make them. The first one is just practicing with these like kind of relative vector sizes, right? We're not out here with a ruler making sure like each one of these match up, but we're developing the skill of being able to kind of like okay, well this one points left and this one points right and they're the same, so those can cancel out, right? It's recognizing that these, like in C, the y components of either one of those are smaller compared to our original one, right? It's recognizing that in E, all 3 y components are about the same. It's just kind of being able to recognize, being able to like see the components of a vector, right? This diagonal vector here, I can see that it points about this much in the x direction, that much in the y, and just kind of like being able to add them in your head, right, and make these logical arguments instead of always just doing the algebra. Usually you will have to do the algebra too, but the logical piece really helps you to be able to check your work and decide where to go next in a problem a little bit quicker. So yeah, let's do some practice with a momentum chart that requires a few different vector sizes, and just practice telling a good story with a momentum chart and using it to solve a problem. All right, so I wrote this problem where I spilled chocolate milk all over a bunch of quizzes, and of course I have no choice but to give them a 0 because I can't read them anymore. And so, of course, I faced retaliation for that, as I should. So I'm rollerblading at 5 meters per second in the positive x direction, and a few students, the victims of my laziness with my chocolate milk, threw 3 eggs at me in the opposite direction. So I'm moving 5 meters per second one way, the eggs are coming at me 20 meters per second in the other direction, and each one of those eggs has a mass of 25 kilograms. And my mass is 60 kilograms. So I am moving slower than the eggs, but I weigh a lot more. They're moving faster. They weigh less. So let's define our system. Well, it's me and the 3 eggs, and we'll say there's no external forces. So no friction, no nothing. That tells us that F net is 0 or delta P total is 0, right? Any momentum change that occurs for any object has to come from somewhere else. We can only have momentum exchange, no total change. So let's try to fill out a momentum chart. Oh, and the goal here, we want to know how much that slowed me down. So the eggs are thrown at me. How much does that change my speed? So let's start with a momentum chart. So we have a row for me, a row for the 3 eggs, and I combine them all together because, again, this is kind of like going back to what we did with those 2 forces where we combine them into a single piece because they just act as one, F net. Here, we can think of it as 3 separate eggs, but really they're all behaving the same way, right? They have the same mass, they're coming from the same direction, they have the same initial velocity, right? So I'm just going to combine them together, and they're going to act. I can just multiply each one of their contributions by 3, Or, I mean, I could also just say I have 1.75 kilogram. Maybe it was an ostrich egg. I don't know. But I'm going to combine them together, and we'll see that that'll work out the same way. So we know the initial state, right? We're given specifics for all of that, all the masses and velocities. So for me, I have some velocity, 5 meters per second, and to the right, and some mass, and so there's my initial momentum. The eggs have an initial momentum in the opposite direction, right? I'm moving in the positive x direction. They're moving in the negative x direction. They're moving a lot faster, but like we said, they also have a much smaller mass. So the momentum arrow for them is going to be, again, in the opposite direction, but a lot shorter. Their speed, or their velocity, is only 4 times more than mine, right? 5 versus 20, but their mass is 1/240th of mine. Right? It's like 60 kilograms versus 1/4 of 1 kilogram. That's much more significant than 5 meters per second versus 20 meters per second. So, I mean, that's kind of intuitive, right? If you're standing there, I mean, that's a good way to think about momentum maybe, is how would I feel this momentum transfer, right? You're standing there, and I'm rollerblading toward you, and I collide with you. You're going to feel that. You'll probably fall over, at least stumble back a bit. If I toss 3 eggs at you, that's not going to throw you up into the air. And like it doesn't, those 3 eggs, even if they're moving fast, they're so light, they have so little mass that they don't really carry very much momentum. So that's a good way, like, just mentally, to think about the scaling of your momentum arrows. Maybe is if I'm going to be hit with the object in question, what am I going to feel more? Which have more momentum? Anyway, you could also just multiply 5 times 60 versus 0.25 times 3 times 20 and see the difference. Anyway, we add those together to get my total initial momentum, and that gives me an arrow that is a little bit shorter than my initial momentum. Right? Our total is a momentum arrow to the right, because mine is a lot larger than the one of the eggs. And since we know there's no net force here, there's no delta P total, our final total momentum has to be the same as our initial. Right? So we already said that whatever momentum is in this system shared between me and the eggs has to stay constant. We can exchange some, but none is being dumped into or taken out of the system as a whole. So to fill in the rest of this, let's do a little work. We don't know what the final state looks like, right? We're only given the initial speeds and the masses, but we don't know what it looks like after the collision. But what is one thing we do know about what happens when someone is hit with eggs? So maybe we don't know quantitatively, but if I throw an egg at someone that is moving, that egg generally does not bounce off. Well, I guess a raw egg, I should have specified. It's not going to bounce, right? It's not going to go pass through them. It's going to stick, right? It breaks and sticks to them. So what that means, we do have extra information here, that my velocity and the velocity of the eggs is the same after the collision. Right? So once the eggs hit me, we know what their initial velocity was, what mine was. We don't know what that final velocity is that we're traveling together, right, in the same direction that I'm going. So I'm going, the eggs hit me, they stick to me, and now I've slowed down a little bit, but now the eggs are traveling with me in this positive x direction. So to write that out, if I'm writing out the final momentum of me and of the eggs, both it's mass times velocity, but our masses, those are different, we know what they are. We don't know what this V final is, but we know it is the same because they stick together. And as we'll see soon, that piece of information that they stick together is crucial to solving the problem. Right? And that's true for all collision problems. If I just give you the initial setup and say there is a collision, I need to know something about how what the final state looks like. I can't just tell you masses and velocities and that there's a collision and have you solve the whole problem, right? Because things can stick together. Things can bounce off of each other. We've seen that. We've seen a lot of problems where there's 5 options for what the final state could look like, and only one of them is impossible. There's 4 valid collisions that could occur. And so to decide between those, we need a little bit of extra information about the characteristics of the system. For instance, are one of the components of the system eggs? In this case, they are. So our v-finals are the same. So what does that mean? Well, one interesting thing we could do, this isn't like an equation I would ever need you to write out, but it's just to show what is the ratio of our final momenta, right? If we have the same velocity, then my momentum divided by the egg's momentum simplifies to just my mass over the egg's mass, right? Because if these are our two momenta, the velocities cancel out because they're the same. And so one way of saying this is the ratio of my momentum to the eggs is 80, but I have 80 times more momentum. Like the magnitude of my momentum is 80 times that of the eggs. So what does that mean? Well, when we're filling in our momentum chart, we know both of these arrows are going to be to the right? But my arrow is going to be a lot longer than the one of the eggs, right? Because if we're moving at the same velocity, I'm a lot heavier, is one way to put it. So if I choose this to be my final velocity, or my final momentum, that's fine. I know it should be a bit shorter than my initial, right? Because the eggs are hitting me and slowing me down, so it should be a little shorter. And then however long that is, the one from the eggs should be a lot smaller. Clearly, this is not 1/80th of that, so we don't need to be that nitpicky. But this is just to kind of represent when we're making these charts, it's just important to keep relative scaling clear enough that you can read it, right? I need to be able to see that this needs to be a little shorter than that. This needs to be a lot shorter than that. So on and so that's the level of detail that we need for these momentum charts, is just does it convey what's greater than what, and are certain things that need to be equal. So once we fill these two columns in, this all makes sense. The eggs were moving this way and then hit me, stuck to me, so now they're moving the other way. And this should probably, we'll see this quantitatively, but this is their final velocity, or final speed rather, is going to be in the other direction, but smaller than their initial, right? Because they were moving 20 meters per second to start with. So no matter what, if they stick to me and I'm slowing down from 5 meters per second, they're going to be moving slower than they were originally, or have a smaller magnitude of their momentum. And then these two add up to, again, our total, which is some momentum in the positive x direction. So lastly, we can fill in the delta p column, which at this point is just vector addition, subtraction, whatever you want to call it. But I go from some initial momentum to something a little bit slower in the same direction. So my delta p is just a little bit in the negative x. And the eggs, they go from moving one way to moving the other. So there's something in the positive x direction turns them around. I deliver an impulse to them in the positive x direction. We could have figured that out two ways, either from just seeing the change from going negative x to positive x, or we could also just say, well, if this is my delta p, the eggs slowed me down a little bit and gave me this impulse, then the impulse I gave to them must be equal and opposite in order for them to add to 0. Because remember, this collision problem with no external force is just describing an exchange of momentum, and there can be no net. All right, so now let's crunch the numbers. When we're evaluating this table, there's a lot of different equations here. I guess there's 6 of them, right? One, down each column, we can do our p initial, this plus this equals that, our delta p, this plus this equals that, so on and so forth. And we can go across our 3 rows, p initial plus delta p equals p final. So there's a lot of different equations we can start with. But in this case, there's really only one that we know we have enough information to solve, and that's our p initial, right? Like I said, we're given the masses, and we're given all the initial velocities. So we can just evaluate what the total initial momentum is. So let's do that. Let's go down the first column, just saying p total initial is the sum of my initial momentum and the egg's initial momentum. So I plug in all the numbers that I'm given. I'm 60 kilograms and moving 5 meters per second in the positive x direction. There's 3 eggs. So again, here I could have just, I could have 3 terms, each 0.25 kilograms, moving negative 20 meters per second. But instead, I'm just going to multiply it by 3, consider them as a unit. It gives the same result. And the other key to mention here is that even though we've simplified to working in a single direction, right? These are all technically vectors, but they're all just plus and minus x, right? So we don't need to worry about components and stuff. The sign is still important, right? It's still important that the sign of my velocity, 5 meters per second, is opposite the sign of the egg's velocity, negative 20 meters per second. Otherwise, they would all be moving. That would represent them all moving in the same direction. So just because you only have one direction considered in a problem, make sure you don't get complacent about keeping track of the signs. Okay, so we get some initial total momentum, 285 kilogram meters per second. Great. So where do we go from that with our momentum chart? Well, let's use the simplest row we have, which is just that P initial plus delta P equals P final. Since delta P is 0, this equation is done, right? Whatever my P initial is, that's what my P final is, because I have no change in momentum. So this is the total amount of momentum that we're working with, and it can't change, right? How that momentum is distributed amongst the objects can change, but the total remains constant. And now, since we know what our P final is, let's try to figure out what the final velocity of me and the eggs was. So we know this piece. We know the total final momentum. So that's equal to the sum of the momenta of me and the eggs in the final state. And here, again, it's the same setup, very similar setup as we did for P initial. It's just mass times velocity plus mass times velocity, except we don't know the velocity, but we do know that they're the same, right? Like I said, that is the key to us being able to solve this problem, that the eggs stick to me, right? If these two V finals were not equal to each other, then we would have one equation with two unknowns, V final me and V final eggs, and we wouldn't be able to solve that. So we need that information that they stick together, or that our final velocities are the same in order to solve it, which now we can, right? Because this is just an equation, V final. There's two of them, but it's the only unknown. And so if I rearrange and solve, then I get my V final is just 4.69 meters per second. So does that make sense? Does that represent a slight slowdown of me due to getting hit by the eggs? Yeah, I started moving 5 meters per second in one direction, 3 eggs hit me, and now I'm moving a bit less than that. And the eggs are also moving at this speed, right? V final represents the speed of me and of the eggs because they're stuck to me. So the eggs were moving very fast toward me, they hit me, and now we're all moving a little bit slower than I initially was in that original direction that I was moving. So to summarize what we had here, the eggs have a small amount of momentum, and I have a lot of momentum in the opposite direction. We hit each other and exchange some, and as a result, now we all are moving in that initial direction, except a little bit slower, because now there's no object traveling in the negative x direction to kind of take away some of mine a little bit, is one way you could think of it. Again, upon collision, we exchange momentum. That caused my speed to reduce and the eggs to change direction, and then afterwards they're traveling all together. So, like I said, the key piece of information is that we know that they stick together. So let's investigate what that means a little bit more. And it turns out that that's going to be closely related to energy in the system, which is something we haven't talked about in the context of motion in collisions yet, right? We've been talking about speed, forces, and momentum conservation, but we haven't talked about energy conservation. So what happens to specifically kinetic energy? We're not going to talk, in this unit, we're not going to talk about like potential energy, thermal very much or anything, but let's look at kinetic energy, the energy associated with motion, because these are motion problems after all. I know we've seen this before, and we worked with, I guess, a more complex version of this earlier in the quarter when we looked at kinetic energy density, right? But now swap out the density with just mass. Kinetic energy is just 1/2 mass times the velocity squared. And it really, velocity, speed squared, it's important that whatever you plug in for v is the magnitude of the velocity. So direction doesn't matter. An object moving 5 meters per second this way or 5 meters per second this way both have the same kinetic energy if they have the same mass. Direction doesn't matter. And that, yeah, the squared should take care of that. But we'll see that when we actually apply things. Let's ask what happens to kinetic energy in this problem. right? So the eggs are traveling toward me, I'm traveling this way, there's some kinetic energy associated with that, and then afterwards, we're all stuck together, traveling at some speed, there's some kinetic energy associated with that. So let's solve it for both and compare. So for my initial state, just 1/2 mv squared for me, plus 1/2 mv squared for the eggs, and same trick here, plug in my numbers, plug in the numbers for the eggs. I'm just multiplying by 3 here, right? That's just 3 of the exact same thing occurring. I plugged in -20, but it doesn't matter. Even though the eggs are moving the opposite direction to me, you can't have negative kinetic energy. Motion in any direction has energy. And so -20 squared is the same as 20 squared. It doesn't matter. It's just the magnitude, their speed. We evaluate that and we get 900 joules. So that's the amount of energy, kinetic energy in the system when the eggs are traveling toward me and I'm traveling toward them. Now let's look at after the collision. Final kinetic energy. The expression is the same. It's just now instead of V initial, we have V final. So let's plug in. Now our V final, we know, is the same for me and for the eggs, right? Afterwards, we're all stuck together, traveling at 4.69 meters per second, and we have the same masses as before. Another way you can think about this is we're all stuck together, so you can consider me and the eggs as one unit. So this is all the same as if I just had one term here, and I just did 1/2 times 60.75 kilograms times 4.69 meters per second squared. That's any way you want to think about it is fine, but the result is 668.25 joules, which is less than we started with, right? So our initial kinetic energy is greater than our final. We lost some kinetic energy in this collision, and we call that an inelastic collision. So when we lose kinetic energy, that's an inelastic collision. And the opposite of that, when we do not lose kinetic energy, is called an elastic collision. So these are the two broad categories of collisions we're going to be looking at, elastic and inelastic. Again, inelastic are when we do lose kinetic energy, and elastic collisions are when we do not. So some key pieces about both. Again, kinetic energy conservation is the big one. Where does it go? Well, it's dissipated into other forms of energy, right? We still have like universal energy conservation. If we're losing kinetic energy, it's got to go somewhere. But think about most collisions that we experience. Let's see, I'm going to drop this pen and it's going to collide with the table, right? We just heard that. That sound took energy to produce, right? A sound wave is like is a pressure wave in the air. That's not free. We had to spend some energy. So that, we know, was at least partially inelastic. Some kinetic energy, one way we can think about that is the pen was moving and then it wasn't and nothing was. So clearly the kinetic energy has changed, but some of that energy went into other systems, including the sound that we heard. There's also thermal energy dissipation, right? When things collide, like they get very hot. So yeah, that's if a car hits something, the crumpling of the hood and it will heat up. Anyway, doesn't really matter. We're not going to ask questions necessarily about where the kinetic energy goes, but it's lost to other energy systems when the collision is inelastic. When objects stick together, like they have the same final velocity, like the eggs did in that problem, that's called perfectly inelastic. That's the maximum amount of kinetic energy that you could lose. On the far opposite end of the spectrum, you have perfectly elastic collisions. That's when they bounce off each other and no energy is lost, right? So our initial kinetic energy is the exact same as our final kinetic energy. That is not really a realistic scenario, right? Think about any collision you know. It makes some amount of noise, some amount of energy is lost to little vibrations in air molecules. It's more of an approximation, a perfectly elastic collision. One way to think about that, like you take a basketball and you drop it, and it's bouncing, and each bounce is successively shorter than the last, right? The energy is going places. We're hearing sound. The ball is stretching a little bit, and that's taking energy, and it's heating up, and energy is bleeding into all these different things, and clearly we're losing kinetic energy because each time it hits the ground, moving slower and slower. So anyway, elastic losing energy, inelastic losing energy, my bad, and elastic kinetic energy is conserved. So like I said, perfectly elastic is this ideal Ke initial equals Ke final. We don't have to always have perfectly inelastic collisions, though, right? It's not like I said, when they stick together, that's like the extreme end. That's perfectly inelastic. That's when we're losing the maximum amount of kinetic energy that we can. However, things can be somewhat in between, right? If I throw a ball at the wall and it bounces off, we're all going to hear that. That's one key way we know, oh, we lost some kinetic energy there because we produced a sound, right? We made some other sort of energy. But it also did not lose as much as it could have. So that is a partially inelastic. We just call it inelastic, but not perfectly inelastic collision, because we could have lost more kinetic energy. We could have saved more, but some was transferred. So that's really it. These two categories of collisions, and like a key that you can look for in problems is that when they stick together, yes, when you're solving it, the key piece is that the V finals are the same, and then when you're evaluating whether it was elastic or inelastic, if they stick together, you know for a fact that it was inelastic. However, otherwise, you just have to check yourself. And even if it is perfectly inelastic and they stick together, you can still check, like we just did, evaluate what's my initial kinetic energy, total, what's my final total kinetic energy, and if they're the same, it's elastic. If they're not, it's inelastic. So I think I've hammered that home enough. But connecting this back to those collision problems, one, I mean, you'll just be asked this, like, was this an elastic or an inelastic collision? But whether it was or not is often a key to solving a problem, right? And this is what determines which of those four options in like a multiple choice collision problem, which of those actually occurs in any given scenario. And that's like, what are the materials of the things that are colliding, right? And what, just other properties of the collision. The elasticity will determine which of the possible momentum conservation scenarios actually occurs. All right, so let's do one practice problem with this. So we have a little piece of space garbage, has some initial velocity in the positive y direction, and then it hits the moon. The moon doesn't react, meaning the moon is just still. It's solid. We're not, so the system is the object, right? Hits the moon, and then afterwards it has some new velocity that's to the right and down. And I'm asking you, based on this information, its initial and final velocity, is the collision elastic, and is momentum conserved? So is kinetic energy conserved, and is momentum conserved? I'll give you a minute or two to investigate. Oh, I guess I should open the poll. All right, let's talk about this one. So I see a lot of spread across the answers, which is good. This is a tricky one to begin with. So let's first talk about momentum. Is momentum conserved here? Well, in a way, it's conserved universally, but for this object in particular, it's not. The object is initially moving up, and then it's ending moving to the right and down. So clearly there is some net change in momentum, right? We need an external force to produce that delta P. So I've said this, but I'm not a huge fan of this language because momentum is always conserved in the universe. The moon would technically react, or the moon would have its velocity change in a tiny amount, or would absorb the impact, something like that. Anyway, momentum is not conserved within our system of just this object because the moon delivers an external force and changes its momentum. What about the kinetic energy? Well, to show the work on here, I'm going to have to give away the answer, but kinetic energy actually is conserved. It's elastic. And let's explain why. Well, we have to check. Our initial kinetic energy, 1/2 mv squared. The magnitude of our velocity is 5 meters per second, so I just plug that in. We get 1/2 times m times 5 meters per second squared. For the final, however, we have this velocity given in terms of components. And just like I said, it's the speed that matters for kinetic energy. We need the magnitude of the velocity. We wouldn't just sum the kinetic energy in the x and kinetic energy in the y. That's not right. It just gives us too much kinetic energy. So yeah, this is just a key here. Whenever you're evaluating the kinetic energy, make sure you have the magnitude of every velocity. The direction doesn't matter. They could be up, down, diagonal, back, front. Just find the magnitude, and then you can add them up. But here, the magnitude of the final velocity is still 5. If we use the Pythagorean theorem, square root of 3 squared plus 4 squared is 5. And so my initial and final kinetic energy are indeed equal. And so this collision is elastic, but momentum is not conserved in this system because there's an external net force from the moon. So that's all I have for you today. Next week, we'll have a quiz on 2D collisions and then start talking about rotations and torques and stuff like that. Have a good weekend and